Chapter 8, Non-Electrolyte Solutions, Section 8.1, Ideal Solutions and Raoult's Law. In an ideal solution of two components A and B, the AB interaction is the same as the AA interaction, and also the same as the BB interaction. So in this case, when we mix liquids A and B, they form a solution, and for each A or B molecule in the solution, they feel the same amount of attraction and repulsion before and after mixing. An ideal solution may contain more than two liquids. For example, over here we can have an ideal solution of three components: H2O, HDO, and D2O, and D denotes deuterium because these three water molecules are isotopic water molecules. They have very similar chemical and physical properties. So a mixture of these three components behave virtually ideally. Now let's look at the Raoult's law. Raoult's law states that the partial pressure of species I is equal to the mole fraction of this species I in the ideal solution multiplied by the pressure of pure liquid I. This star denotes pure. So again, Raoult's law applies to an ideal solution. X sub I is mole fraction of species I in the ideal solution. Star stands for pure. Pi star is the pressure of the vapor on top of pure I, and then P sub I is the partial pressure of I on top of an ideal solution that contains species I. We have this Raoult's law because the vapor pressure of species I is proportional to the evaporation rate of species I, and the evaporation rate of species I is proportional to the mole fraction of species I in the solution. So that's why you have the mole fraction of I here. For example, let's look at an ideal aqueous solution of glucose. Well, in the real world, it's not an ideal solution, but hypothetically, let's look at this example. Let's assume the interaction between water and glucose is the same as the interaction between glucose, and also the same as the interaction between water and water. So approximately, we say it's an ideal solution. So over here, let's see. We have pure water, and the water molecules in the liquid phase may enter the gas phase. That's called evaporation. And also, the water molecules in the gas phase may enter the liquid phase. That's condensation. And at the equilibrium between the condensation and the evaporation, we can measure the pressure of water, pure water. So we have corresponding P of water star over here. What if we add glucose into this water? When we add glucose in the water, we lower the mole fraction of water. Let's have a numerical example. Let's say we added glucose, so the mole fraction of water drops to 80% of the initial mole fraction. That means just 0.8, because initially we have pure water, the mole fraction is 1. Right now the mole fraction is only 0.8 after the addition of glucose. When the mole fraction of water drops to only 0.8, that means on the surface of liquid, we also have the mole fraction of water drop to 0.8, 80%. And because the evaporation of water is proportional to the mole fraction of water on the liquid surface, that means the evaporation rate now is only 80% of the evaporation rate of pure water, so it drops. And adding glucose does not really change the condensation rate. So now, right here, we do not have an equilibrium. The condensation is now faster than evaporation because the evaporation rate is only 80% of the previous evaporation rate. When you have a higher condensation rate than the evaporation rate, you will have lower pressure of water in the gas phase. Eventually, the liquid phase and gaseous phase of water will reach equilibrium, and at that point, the partial pressure of water in the gas phase drops to also 80% of the initial condensation rate. And that's when the condensation and evaporation are equal again. They are equal again, but they are now only 80% of the initial values of pure water. And that explains why the partial pressure of water on top of an ideal solution is equal to the mole fraction of water in the solution multiplied by the pressure of pure water. Again, we look at three scenarios over here. So scenario A, B, and C, we can see in A, we have pure water. The evaporation rate equals the condensation rate. B, right after we add glucose, you can see the down arrows are more than the up arrows. That means we have faster condensation than evaporation. And that means overall, we'll have fewer water molecules in the gas phase. C, in the end, the evaporation rate equals the condensation rate again, but their values are now only 80% of the initial values. I'm assuming the mole fraction of water over here is only 80% of 1. Okay, so again, if we look at the arrows, you can understand we have over here the condensation equals evaporation, over here the condensation equals evaporation. But if you compare this to equilibria, you can see over here we have 5 arrows up, 5 arrows down. Over here 4 arrows up, 4 arrows down. So that's because again the mole fraction of water drops to 80%, which will reduce the evaporation rate, alright, to only 80%, and eventually the condensation rate should match the evaporation rate, and the condensation rate is proportional to the partial pressure of water in the gas phase. So eventually the partial pressure of water on top of this solution will have to be reduced to 80% of the initial value as well. In an ideal aqueous solution, the vapor pressure of water is the mole fraction of water multiplied by the pressure of pure water under the same condition, regardless of the identity of the solute. As long as we can assume the attraction between the solute and water is the same as the attraction between the water molecules, and that means we're not really changing the attraction and repulsion felt by each water. In this case, the evaporation rate of water over here, the rate of evaporation, is equal to the mole fraction multiplied by the evaporation of water of pure water. So right now we have this equation. Again, we can write this only if we assume adding a solute does not really change the amount or the magnitude of attraction and repulsion for the water molecules. And then we have this. That means the evaporation rate is only proportional to the mole fraction. I mean, if we have lower mole fraction, we have fewer water molecules on the surface, and we have slower evaporation rate. Again, the star denotes pure substance, and R is the rate of evaporation here. When the liquid and gas phases of water are at equilibrium in an aqueous solution versus the equilibrium in pure water, we have two equations. In an ideal aqueous solution, we have this. The evaporation rate is equal to the condensation rate for the water in ideal solution. So over here in a pure water at equilibrium, also we have the evaporation rate equals the condensation rate. The difference between these two equations is the top equation is for an ideal aqueous solution, the bottom equation is for pure water. Because the condensation rate is proportional to the vapor pressure. I mean, we can understand if we have a higher vapor pressure, we have faster condensation rate. When we have lower vapor pressure, we have lower condensation rate. And then we have this equation, the condensation rate of a ideal aqueous solution over the condensation rate for pure water is just P over P star. P is the vapor pressure of water in a solution. P star is the pressure of pure water. And because of this, and then we can write out this equation because the condensation rate is equal to the evaporation rate. And then we can write out this ratio between the condensation rates is equal to the ratio between the evaporation rates. And also this is equal to X times the evaporation rate for pure water. It comes from here. I was replacing the rate of evaporation of water in an aqueous solution is equal to the mole fraction times that of pure water over here. So this is really X. And now you can see P over P star is this, and this is X. Now we just proved Raoult's law for an ideal solution, which is just this: P over P star is equal to X, or P is X times P star. P star is the pressure of pure water. X is the mole fraction of water in a solution, and this P is just the partial pressure of water on top of that solution. And again, we can use Raoult's law for ideal solution. For a real solution, this equation is approximately true. Again, in an ideal solution of two liquids A and B, A-B interaction is equal to A-A interaction and also equal to the B-B interaction. That ensures that in the solution we have both A molecules and B molecules, and in the solution each A is surrounded by some A molecules and some B molecules, same for each B molecule. But in a solution, we say the magnitude of attraction and repulsion felt by each A or B molecule remains unchanged before and after the mixing. Because of this, I mean, even though in the solution A is now like, for example, surrounded by 40% of A and 60% of B, but because the AB interaction is the same as AA interaction, therefore the mixing did not really change the attraction or repulsion felt by each A. Now let's look at Raoult's law again. The partial pressure of species I on top of a solution of I is equal to the mole fraction of I in the solution in the liquid phase multiplied by the pressure of a pure I. Again, X stands for mole fraction and star stands for pure. Raoult's law is actually one of the colligative properties that depend on the quantity but not the identity of the solute in the ideal solution. As long as this solute satisfies this statement, we does not really care about the identity of the solute. Now let's look at one numerical example problem 8.1.1. At room temperature, the vapor pressure of pure 1-propanol is 0.0199 bars. The vapor pressure of pure 1-butanol is 0.0058 bars. Using Raoult's law to calculate the partial pressure of these two chemicals above the surface of the liquid mixture of this 1-propanol and 1-butanol, and calculate the total vapor pressure. We're given the mole fractions of these two components. They are 0.4 and 0.6. We can also calculate the mole fractions of these two chemicals in the gas phase. Now let's assume the liquid mixture of 1-propanol and 1-butanol is approximately an ideal solution because they have similar water structures. We're just assuming the interaction between 1-propanol and 1-butanol is approximately the same as interaction between two 1-propanol molecules. It's also approximately the same as the interaction between two butanol molecules. Of course, the interaction would be a little bit different, but again, we're saying approximately. It's an ideal solution. Alright, and now we can compute the partial pressure of 1-propanol and the partial pressure of 1-butanol. Separately, using Raoult's law, we're going to use this equation. So we copy this equation here. For propanol, we have the mole fraction of propanol in the solution, which is 0.4, multiplied by its pressure, the pressure of pure propanol, and we got a number here. Same for butanol. We use the mole fraction of butanol in the solution, 0.6, multiplied by the pressure of pure butanol. We get another number. Now we have the total pressure. We just sum it up. In the gas phase, we have two components. We just need to sum up their partial pressures. We get this 0.01144 bar. This is really between the vapor pressures of pure propanol and pure butanol. So this number is smaller than the vapor pressure of pure propanol. It's higher than the vapor pressure of butanol. Alright, it does make sense because again we are using this multiplied by our mole fraction. We're using this multiplied by the corresponding mole fraction and sum it up, and therefore the final total pressure has to be smaller than this larger number and greater than this number. Now we can compute the mole fractions of the gas phase. It's going to be 796 over 1144, and we get 0.696 for propanol, 0.304 for butanol. You can see this mole fraction is actually greater than this mole fraction. So why is that? Well, we're talking about propanol, right? Its mole fraction in the liquid phase is 0.4, in the gas phase it's 0.7. Why such big difference? Well, it's just propanol has a larger vapor pressure. It's easier to evaporate propanol, and that's why the partial pressure in the gas phase of propanol versus the partial pressure of butanol is greater than the ratio between these two chemicals in the liquid phase. In an ideal solution of A and B, again the AB interaction equals the AA interaction. It also equals the BB interaction. In that case, we can use Raoult's law, which is this equation. The partial pressure of species I equals its mole fraction in the solution multiplied by the partial pressure of multiplied by the pressure of pure I. Now let's do some derivation. If a species A obeys Raoult's law, and then we have this equation. That means the chemical potential of A in a solution is equal to the chemical potential of pure A. So the star symbol denotes pure substance, and then plus a correction, RT times the natural logarithm of the mole fraction of A in the solution We'll do some derivation to prove this. The above equation can be proven by comparing two different scenarios of the liquid-gas equilibrium. What two cases? In one case, we will have pure A. In the other case, we will have an ideal solution of A. Alright? So first, case A, pure A is at equilibrium with just gas A, and gas A has a pressure of PA star. Again, PA star, that means the pressure of pure A. So we have this equation. Alright, for the gas phase, mu star. For the gas phase, we have this equation. For the chemical potential of the gas phase, this is the chemical potential of pure A in the gas phase under 1 bar condition, plus this pressure dependence. The pressure dependence is RT times the natural logarithm of PA star over P naught. If you don't recall how we got this, just remember for a pure substance, d mu is equal to dg, and d mu is equal to dgm, the differential of molar Gibbs energy, and dgm is negative molar entropy dt plus molar volume dp when the temperature is constant. dgm is simply molar volume dp, and we can integrate both sides and you will see a logarithm here. The reason is, for ideal gas, molar volume is simply RT over P. You're integrating RT over P dp, and then that's why you have this pressure dependence in the form of the logarithm of a ratio between the actual pressure over P naught. Again, because we use P naught as the standard state, and this mu naught is the chemical potential of gas A when its pressure is 1 bar. Alright, that's why we have this equation. When pure A has a liquid phase and a gas phase, and these two phases are at equilibrium with each other. Therefore, the chemical potential of A, this is pure liquid A, is equal to the chemical potential of gas on the right hand side. Now, what if it's in a solution? So if it's in a solution, we will actually put this solution in the superscript over here. This is the chemical potential of A in a solution. It's still equal to a similar equation here. The only change we need to make is over here, this is PA star. Over here it should be X of A times PA star, because over here it should be the partial pressure of A on top of the solution, and based on Raoult's law, that's just X of A times the pressure of pure A. So now we're going to compare these two equations. They look very similar to each other. On the left hand side we have the liquid phase, on the right hand side we have the gas phase. So we're going to take the difference. We're going to use this left hand side minus this left hand side, and we have this here, and we're going to use this for the gas on top of solution minus this chemical potential for the gas on top of pure A. We take the difference between these two. What's the difference? It's just right here. Therefore, you can see the chemical potential of A in a solution minus the chemical potential of pure A liquid is simply RT times the natural logarithm of the mole fraction of A. And we have this equation. Now, the lower the mole fraction, the lower the chemical potential, and this is why red cells are placed in pure water. So you have a cell membrane separates pure water outside and a solution inside. So when you have a aqueous solution, the mole fraction of water is less than 1. That means the chemical potential of water inside the red cell is lower than the chemical potential of pure water outside, and the water flows into the lower chemical potential region from higher chemical potential region. That's why pure water can flow into the cell due to this chemical potential difference, and eventually it can burst the red cells. We have simpler examples. Let's say you have pure water, so you have a portion of pure water, you have a portion of aqueous solution, And now let's mix this, and you can see pure water molecules will move into the aqueous solution, right? It's gonna dilute this further dilute this aqueous solution. And later we're gonna see another application due to this called osmotic pressure.